Hello, electronics enthusiasts. Today on ElectroMaster, we've got a faulty switch mode power supply from a professional Bizerba machine on the bench. Stick around until the end to see how we diagnose, test, and bring this essential component back to life. Loudspeaker: if you enjoy technical content and step-by-step electronic repairs, don't forget to like, subscribe, and hit the notification bell. As always, I begin with a careful visual inspection of the power supply, looking for any obvious signs of failure, burnt components, swollen capacitors, cracked solder joints, or signs of overheating. This step helps pinpoint potential issues before moving on to electrical diagnostics. I've checked the fuse, and it's in good condition. It's not blown and shows no signs of burning. So, we can rule out a triggered protection due to an obvious short circuit. I've also checked the input varistor, and it's within normal parameters. There are no signs of mechanical or thermal damage, which means the overvoltage protection hasn't been triggered. I've checked the primary DC circuit, and it's not shorted. The resistance between the positive and negative rails after the bridge rectifier is within normal range, indicating there are no direct short circuits on the main power bus. Now I'm moving on to checking the two power MOSFETs that drive the chopper transformer. I'll test each transistor individually to check for shorts between drain, gate, and source, and to make sure they are not damaged or internally shorted. After testing, both power MOSFETs are in good condition. There are no shorts between terminals, and they respond correctly to gate testing. So, we can rule out these transistors as the source of the fault. Now I'm moving on to checking the rectifier diodes in the secondary circuit. I'll test each diode individually to ensure none are shorted or open, as these components are critical for converting AC voltage into stable DC output. The rectifier diodes in the secondary are in good condition, with no shorts or opens. Therefore, they are not the cause of the fault. Now I'm identifying the 230V AC input pins and will solder a cable to connect power, so I can proceed with further testing of the power supply. I'm connecting the power supply to 230V AC and will check if it outputs voltage on the secondary. There is no voltage present in the secondary DC circuit, indicating an issue in the conversion stage or a faulty component within the power path. I will discharge the capacitors in the primary circuit to avoid the risk of electric shock and to ensure safe working conditions during the repair. Now I'm moving on to identifying the integrated circuit that controls the power MOSFETs. I've identified the integrated circuit. It's an SG2525A, a pulse width modulation PWM controller, responsible for driving the MOSFET transistors in our power supply. Now I'm identifying the power supply pins of the integrated circuit to check if it is receiving the correct voltage. The integrated circuit is not receiving power, which could be the main reason why the power supply is not functioning properly. I'm checking the power supply path to identify the source of the voltage that should feed the integrated circuit. I realized that this power supply uses an external power source for the integrated circuit, meaning that for proper operation, the IC needs to receive voltage from an additional supply. I'll connect an external 12V DC power supply to feed the integrated circuit, since I've identified a 25V electrolytic capacitor on the power rail. This indicates that the normal operating voltage is lower, in this case, 12V, and the higher capacitor rating, 25V, is used to provide a safety margin. It's standard practice in electronics to use capacitors rated at least 20 to 30% higher than the actual circuit voltage, to prevent electrical stress and increase component lifespan. I've connected the external 12V supply, and now I'll use the oscilloscope to check for a gate drive signal on the MOSFETs. Specifically, I'm looking for a PWM, pulse width modulation, waveform generated by the SG2525A IC. If the signal is present, it means the control section is working properly and is correctly driving the transistors. As you can see on the oscilloscope screen, we have a clean PWM signal on the MOSFET gate, which confirms that the SG2525A integrated circuit is operating correctly. Now I'll reconnect the power supply to the 230V AC mains and check if we have output voltage on the secondary side, indicating that the supply is starting to work properly. Pleasant surprise! We now have 24V present on the secondary output, a clear sign that the power supply is working properly after powering the control circuit. It seems that this power supply also includes an EOFF control circuit that drives a switching transistor. This transistor is responsible for enabling or disabling the 24V DC output on the connector, based on an external control signal. In other words, the output is electronically switched and not always active, which is an important detail to consider during testing and troubleshooting. I've identified the EOFF control circuit. All I need to do now is apply a +12V signal to the control pin to switch the transistor into conduction state. This will activate the 24V DC output on the connector. This type of control is commonly used in industrial equipment, where the power output is enabled only when an external logic signal is present. As you can see, the switching transistor responds correctly to the external signal. When 12V is applied to the control pin, the transistor switches on and the 24V output appears on the connector. When the signal is removed, the output is disabled. This confirms that the EOFF control circuit is working perfectly. All I can say is that in this case, the power supply was previously misdiagnosed by the technician who attempted to repair the equipment. It happens, sometimes issues are misunderstood, or key details are overlooked. That's why a systematic approach, based on proper measurements and step-by-step verification, is essential in electronic troubleshooting. That's it for today. We've shown that with a logical approach and proper measurements, even a power supply initially considered faulty can be brought back to life without unnecessary part replacements. If you enjoyed this video and want to learn more about switching power supply repair and electronic diagnostics, don't forget to like, subscribe to ElectroMaster, and hit the bell so you won't miss future episodes. Until next time, happy soldering and troubleshooting.